Hello everyone, welcome to quick revision series of strength of materials. In this video, I will be discussing about shear stress distribution. First, we will be seeing what is the equation of shear stress and how to use it. Next, the shear stress distribution for different cross sections. Next, I will be discussing what is the relation between maximum and average shear stress for different cross sections. Now, let's see how to find shear stress at a particular distance from the neutral axis. Here in this case, we have taken a simply supported beam with a trapezoidal cross section. The shear stress at a distance y from the neutral axis is given by SA y bar by I into B. Now let's see each and every term in detail. First, suppose if they are asking shear stress at a distance y at a section which is at a distance of x meters from the left support, then S is nothing but the shear force at that section XX. Here in this case, if P is the loading, the reaction here is P by 2 and P by 2. So, shear force at that section X is P by 2. Now, what is A? A is nothing but area of cross section above the point at which shear stress is required. Here, we are finding shear stress at a distance y from neutral axis. That means area above this point is this area. Next, what is y bar? Y bar is nothing but centroidal distance of area from the neutral axis. Here, this is, we have seen that this is the area of cross section to be considered. Now, y bar is nothing but, for this area, centroid will be somewhere here. The distance of this centroid from neutral axis is given by y bar. Now, what is I? I is nothing but moment of inertia of the cross section above the neutral axis. That is, moment of inertia of this total cross section about the neutral axis is given by I. Let's see what is B. B is nothing but at a distance y, we are finding stress at a distance y. So, at a distance y, what is the width of cross section? Okay, for suppose if they are asking at a distance some k from neutral axis, at this particular distance what is the width of cross section is given by B. Okay, in brief, S is the shear force at that particular section, A is area of cross section above the point where we are supposed to find the shear stress, y bar is distance from the neutral axis to the centroid of the area, I is moment of inertia of the whole cross section, B is width of the cross section, like where we need to find the shear stress. So, we have seen how to find the shear stress at a particular distance from the neutral axis. Now, let's see what is the direction of shear stress. Let's take a cantilever beam. If we draw SFD for this beam, it looks something like this. That means there is shear force acting throughout the beam. Because of this shear force, there will be a shear stress generated. This shear stress will be in longitudinal direction. If we take some part of this beam, the shear stress generated will be in this direction, that is in longitudinal direction. This is the actual shear stress generated. To compensate this longitudinal shear stress, there will be a complementary shear stress acting in direction of the load. So, when there is a load acting on the beam, the actual shear stress will be in longitudinal direction and the complementary shear stress will be in the direction of load acting. Now, let's see the variation of shear stress in case of rectangular cross section. We have seen that shear stress at a distance y from neutral axis is given by this formula. By using this formula, we will be finding what is the shape of shear stress distribution diagram in case of rectangular cross section. Now, let's see what is A. Here, we are supposed to find what is the value of shear stress at a distance y from neutral axis. So, area should be taken like above the cross sectional area above the point y, that is this area. It is given by B into AB. Here, AB is nothing but AO minus BO, which is nothing but D by 2 minus Y. So area is B into D by 2 minus y. Now let's see what is y bar. Y bar is nothing but distance from neutral axis to centroid of the given area. Here centroid of the area will be at the center of AB because this is a rectangular cross section. That means we know that AB is D by 2 minus y. The centroid will be at a distance the half of AB, which is D by 2 minus y by 2. Finding y bar, that is total distance D by 2 minus AB by 2, we will be getting this. By taking minus inside, we will be getting D by 2 plus y whole divided by 2 as y bar. We know that I must be taken about the neutral axis. So it is BD cube by 12. Now let's see what is B. B is nothing but width of the cross section at a distance y. Here in rectangular case, width is constant. So directly we can take B as width of the rectangular cross sections. Here in this case it is B. By substituting A, y bar, I and B in this formula, we will be getting tau as this one. Here there is a parabolic variation. From this we can observe that the shear stress distribution is a parabolic variation. Substituting y equals to 0 in this equation, that is at neutral axis, finding what is stress at neutral axis, we will be getting, see, we are subtracting y square from d square by 4. That means at y equals to 0, we will be getting tau max, which is equals to 3 by 2 into S by BD. By substituting y equals to plus d by 2 and minus d by 2, that is at top and bottom surface, we will be getting tau as 0. The final distribution diagram looks something like this, which is a parabolic variation with maximum at neutral axis. Okay, this is tau max. Here let's see what is S by BD. S is nothing but shear force acting at that particular section. BD is nothing but area of cross section. That means dividing S by area, it is nothing but tau average. So here in case of rectangular cross section, tau max is nothing but 3 by 2 times tau average. You have to remember this equation because in exams generally they will be asking what is the ratio of tau max and tau average in case of rectangular cross section or in case of circular cross section or something. We have to remember this 3 by 2. We have seen in case of rectangular cross section what is the value of tau max. In case of rectangular cross section, tau max is occurring at neutral axis only. So at the neutral axis, the value of shear stress will be tau max itself. By using same procedure, we can find the shear stress variation in case of circular cross section also. In case of circular cross section also, the shear stress variation will be a parabolic variation with maximum value at neutral axis. That means tau at neutral axis is equals to tau max, and we will be getting that value as 4 by 3 times S by pi r square. That means tau max is 4 by 3 times tau average. Here pi r square is nothing but area of cross section, S is shear force. So S by area is nothing but tau average. So in case of circular cross section, tau max is 4 by 3 times tau average. Now let's see in case of triangular cross section. In case of triangular cross section, the shear stress variation looks something like this. Here in this case, the neutral axis will be at the distance of 2h by 3 from the tip of the triangle. We know that neutral axis of neutral axis passes through centroid of the triangle. We know that centroid of the triangle lies at h by 3 from the bottom surface and 2h by 3 from the tip of the triangle. Here, the tau max won't be at tau neutral axis. It will be above the neutral axis. The variation looks something like this. In case of triangular cross section, tau max will be at the distance of h by 2 from the tip of the triangle. We have to remember this. By finding what is the value of tau max, it will be 3 times S by BH, which is 3 into S by BH by 2 into 1 by 2. Okay. We know that S by BH by 2 is nothing but S by A, which is nothing but tau average. That means in case of triangular cross section, tau max is 3 by 2 times tau average. Okay, this is the value of tau average. Okay, that is S by BH by 2. And we'll be getting tau neutral axis as 8 by 3 times SBH. We can observe 8 by 3 is something 2 point something, which is less than 3. See, tau neutral axis is less than tau max, which is 8 by 3 times S by BH, whereas tau max is 3 times S by BH. Now let's see the shear stress variation in case of diamond section. Diamond section is nothing but a square section which is rotated in such a way that one diagonal is in horizontal direction and other diagonal is in vertical direction. So in case of diamond section, the shear stress variation looks something like this. Here in this case, tau at neutral axis is not equals to tau max. The tau max occurs at some distance from neutral axis, which is h by 8 from neutral axis or 3h by 8 from vertex of the diamond section. You have to remember this. Now let's see what is tau average in case of this section. Now we know that tau average is given by shear force acting on that section by area of cross section. Here in this case, this is a square section with diagonal h. We know that in square section, both the diagonals will be equal. To find side, we know that diagonals diagonals bisect each other perpendicularly. By using Pythagoras theorem, we can find side of a square as h by root 2. That means area is given by h by root 2 whole square, which is h square by 2. So the tau average is nothing but s by 2s by h square. Okay. By using shear equation, we can find tau max as 9 by 4 times s by h square. And tau neutral axis is nothing but tau average. In case of diamond section, tau neutral axis is nothing but tau average. So finally, the most important thing to be remembered in case of shear stress variation is, like in case of rectangular cross section, the tau max is 3 by 2 times tau average. In case of triangular cross section, tau max is 3 by 2 times tau average and tau neutral axis is 4 by 3 times tau average. In case of circular cross section, tau max is 4 by 3 times tau average. In case of diamond cross section, tau max is 9 by 8 times tau average. We have to remember these values. These are very important values. They will be asking in exam directly. For example, if they ask, find the tau max in case of triangular cross section of area A, which is equals to 10 centimeter square, and the shear force acting is some 10 Newton. Okay, we have to find tau max. So we know that in case of triangular section, tau max is given by 3 by 2 times tau average. That means 3 by 2 into tau average is nothing but shear force acting by area of cross section. That means it is equals to 3 by 2 Newton per centimeter square. That means without remembering the formula of tau max, by remembering the ratios, we can easily solve the problems. So don't forget to remember these ratios. Now let's see the shear stress variation in case of I section. If we observe the flange region of I section, it is rectangular in shape. It will be a parabolic variation from top to junction. If you observe, just above the junction, the width is capital B, and just below the junction, the width is small b. We know the shear stress formula is S A y bar by I into B. Here, B is decreasing from capital B to small b. So, shear stress will be increasing. That means, just above the junction in flange region, shear stress will be this value, and just below the junction in web region, shear stress will be this value. There will be a sudden increase in shear stress. Now, if we observe the web portion, this is like rectangle only. So, the shear stress variation will be a parabolic variation with maximum at maximum at neutral axis. The main important point to be remembered in case of I section is this thing. That is, what is shear stress in flange region just above the junction, and what is shear stress in web region just below the junction. Now let's see how the variation of shear stress looks in case of T section. Similar to I section, in flange region, the variation will be in parabolic shape. Just above the junction, the shear stress will be here, and just below the junction, that is in web region, the shear stress increases. And after this, in web region of T section, it is similar to rectangular section, so the shear stress variation will be parabolic with maximum at neutral axis. Now let's see shear stress variation in case of H section and plus section. If we observe this is similar to rectangular section, so shear stress variation will be a parabolic one. Here, just above the junction, width is, suppose small b, and just below the section, width is capital B. Here, width is increasing from small b to capital B. We know the shear stress formula is SA y bar by IB. As the width is increasing from B to the width is increasing from small b to capital B, there will be a decrease in shear force. Here, the shear force is decreasing from here to here. And after this is a rectangular variation. I hope you understood this. With this, I'll end this video. If you find my video useful, please share it with your friends. And if you like my content and find it interesting, please don't forget to subscribe to my channel. Thanks for watching.